So this is chapter 4 or chapter 17 if you follow in the book. So complex differentiation. Right. So first of all then, if we let a function f from D, where D is a subset of the complex plane, to C, so D is an open subset of C, then the first definition, so definition 4.1 or 17.1 in the book, part A defines complex differentiable. So f is called complex differentiable I put complex in brackets, so if it's clear from the context, then it's okay to say differentiable. Yeah, if not, say complex differentiable. And this is at the point z0, which clearly must be in D. And this is if the following limit exists. Okay. And again, this is very similar to what you've seen in real analysis, but now functions are in terms of complex variables. Right, so if df at z0 dz, so the notations in the complex case are also similar, or we can use f prime. Okay, but the limit then is the limit as z tends to z0, the point at which we're looking at the differentiability of f of z minus f of z0 over z minus z0. So let's put this into context. So this function f is called complex differentiable at the point z0 if this limit exists. Yeah. Okay. Then part B, so this is part A, then part B of the definition defines a holomorphic function. Okay? So we call the function f holomorphic in D. And this is if f is differentiable at every point in D. Okay? So if f is differentiable at every point z in a domain D. Okay? So we use the term differentiable at a point, holomorphic if we've got differentiability at every point in the domain. Okay? If a function is differentiable on the whole of C, we call it entire. So if f is holomorphic on the whole complex plane C, we call the function an entire function. Okay, so a few definitions to get us started. And now we're going to see some results. And again, these results are similar to the real case. So the results should look familiar. And in fact, we prove them in the same way, although I'm not going to prove the results that follow. Right, so the first one then is corollary 4.2, which is 17.2 in the book. And if we have a function f, again from D to the complex numbers, if this function is differentiable, at the point z, then it's continuous at this point. Actually, this is z0, yeah. Just to be consistent with notation. Then f is continuous at z0, okay? And again, you will have seen similar result in real analysis. And then the next result, so this is proposition 4.3, 17.3 in the book. So if we let two functions, f and g, be differentiable at the point z0, and if we have a complex number a, okay, then what we get is the sum or difference of f and g, a multiplied by f, yes, so the complex number multiplied by the function f, and the product of f and g, are also differentiable at z0. Okay? These are differentiable at the point z0. And we have the following results, which I will state on the next board. And again, these are analogues to the real case. Right, so first of all, the derivative of a sum or difference of two differentiable functions is the sum or difference of the derivatives. Yeah? So essentially then f plus or minus g prime at z0 is equal to f prime at z0 plus or minus, yeah, whichever the operation is, g prime at z0. Okay? And then for multiplying f by a complex number a and taking the derivative, well, what we can do in this case is just take the derivative of the function and then multiply by a afterwards. Okay? So this is equal to a f prime at z0. Yeah? And then with the product, we have a similar result as we've got in the real case. So we've got Leibniz rule or the product rule. Okay? So this is equal to f prime at z0 multiplied by g at z0 plus g prime at z0 multiplied by f z0. Yeah. Okay, so the results you've seen in the real case these ones extend to the complex case. Right. What about then the derivative of a quotient? Again, we have a similar result. So let's look at this next. But we must ensure that the function where dividing by is not 0. So if this is the case, then the quotient is differentiable. Okay? And we have the following result, which is an analog of the quotient rule. So we have that f over g prime at z0 is f prime z0, so differentiate the function on the top, multiplied by g z0 minus g prime z0 multiplied by function on the top, f z0, and as usual, this is all over g z0 all squared. Yeah, so this is the quotient rule for the complex case. Right, the next result, which is probably the one we will finish with today, is an analog of the chain rule. And this is proposition 4.4. Or 17.4 in the book. Right, so if we let a function f from D1, to again a subset of the complex numbers, to C, if we let this function be differentiable at the point z0, which clearly must be in D1, and a function g, whose domain is D2, to the complex numbers, be differentiable at a point W0. So be differentiable at W0, which is in the domain of the function D2. Yeah. Right, but further, and we need the following conditions so that we can define the chain rule. Right, so suppose that f of D1 is a subset of D2 and f of Z0 is equal to W0. So we must have this so that we can define the composition, yeah? So remember the chain rule is differentiating the composition, yeah? Right, so then the composition GOF, so this will go from D1 and then it'll go to D2 and then to C, yeah? This is differentiable so long as we've got these conditions. At Z0, and we have the following result. And here is then the chain rule. So G composed with F prime at Z0 is equal to G prime of F of Z0, and then we must differentiate inside the brackets, yeah, as it were. So we multiply by F prime of Z0, okay? Right, so remember, so this is the analog complex case of the chain rule, and there's just one remark that follows on from this result. And it's a remark about polynomials and rational functions in the complex case. Right, so the final remark, so all polynomials are differentiable on C, and rational functions which we denote by H. So remember, rational function is quotient of polynomials, so f over g are differentiable on C, but we must be careful that we exclude any points where g is 0. So C minus the point z such that g of z is equal to 0. Okay? Right, well that's a good place to stop today, and I'll see you tomorrow. We'll continue then.